Hey, I'm back again. Forrest Mormon from Wellington, Ohio. Welcome. We're here to give you the details on the Tesla coil which you saw run last night. I'm a tool and die maker engineer, and I have been so for the last 47 years of my life. It's a vocation that I like doing, and at age 60 now, I'm starting to teach myself electronics. In fact, I spent all last winter teaching myself electronics. I have my own manufacturing firm in Wellington, Ohio called Tape Incorporated, and we have 22 guys working for us. There's not a whole lot that I can't do. I built this barn, I built my house, I built the Tesla coils. There's another Tesla coil here, a secondary, another secondary here I wound for a guy here not too recently. I built this Tesla coil that you saw last night. It took me about 4 weeks. I started it about 4 weeks ago. I did the secondary first. I started getting the basic ideas on the design concepts and the size of the toroid and actually how I could build this thing. I've spent the last probably 10 years collecting components like capacitors, coming up with a distributor design, which is the rotary spark gap. I call it a distributor, which is a massive distributor. Rotary spark gap design, and how to actually make everything. It's quite an undertaking to build a Tesla coil from start to finish. I've built some smaller ones, but it's quite a huge undertaking because you have to think through the entire process of assembly, construction, engineering. And do you have the equipment to get it done with? I know a lot of people they struggle that don't have the equipment, and I have to say this: if you're super interested in Tesla coils, go to a Teslathon locally in your area and find out and talk to people and ask questions. One thing I have to say about all of us in this arena: not many of us have had college background. We have the will and the desire to build stuff. And that's the most important key. You have the will and the desire. If you have the will and the desire, you'll find a way and you'll educate yourself in the process. And the only way you will learn is to learn by failure. But that's just the way things go. All right, let's talk a little bit about the Tesla coil. I did build the secondary first. It was made out of 12 3/4 inch OD PVC pipe, just like you can get at your local building supply place. It was wound with 18 gauge copper wire. The primary consists of 1/2 inch copper tubing, and I think there's 13 or 14 turns on there. We'll take a look at that here shortly. The toroid is made from 3.5 inch foam sheet. I got the idea from a website called HV Tesla. That foam sheet looks like this. It's just a plain old foam sheet, 3.5 inches thick. And I'll get into the details here a little bit later on. The toroid weighs about 50 pounds. It only took me 2 weeks to build that thing. I do have a design here, and I'll be glad to share that with you. It has a fiberglass. So I built the substructure all out of foam. And because the foam was so easily dentable, I covered it in a skin of fiberglass, a very thin fiberglass sheet, I should say a blanket, and then put the epoxy resin on it and rough sanded it and filled it some more, and then I put the aluminum tape over it. You wouldn't think that the aluminum tape would hold up with this much intensive arc coming off of it, but it doesn't bother it one bit. And it does make a wonderful looking toroid. I built the secondary and the toroid first, and I had to get those two completed, and I had to find out the resonant frequency of the secondary and the toroid as a unit, plus a 10-foot leader, which I expected as an arc to come off of this thing. When you do try and find the resonant frequency of a Tesla coil, you have to include the arc length. The arc length is actually part of the resonant frequency. So, and you have to be realistic about what you can achieve. I knew that this Tesla coil could reach 10 feet by looking at others and talking with other people. A smaller Tesla coil like this one is not going to go 10 feet. It might go 18 inches, 2 feet maybe, but that has to be taken into account when you do the resonant frequency. So you put a little piece of copper wire on here, stretch it out 2 or 3 feet, and then take a look at the resonant frequency with a oscilloscope and a signal generator. And then when you tune the primary, now I must back up and say this. When you tune a secondary and a toroid, they have to be away from the primary. They cannot be with the primary because the primary has an effect on this. The human body cannot be near this because your body acts as a big capacitor sink as well and will change the frequency. So you have to be way away from it. I'm going to say 4 or 5 feet and and do your testing away from it and find out what that resonant frequency is. Now, when you do the primary can actually be around the secondary. That doesn't seem to have much effect on the resonant frequency. So, find the resonant frequency of the secondary and the toroid and the arc length, and then match the primary frequency to that. This Tesla coil happens to be resonant at 53 kilohertz, 53.0, 53.02. It doesn't matter. You can actually move the tap on that primary about a foot in either direction. It does have a little bit of change, but the most effective one is right where the oscilloscope tells you that the resonant frequency is at. This Tesla coil has an asynchronous rotary spark gap. In other words, when the rotary spark gap rotates, it is not in synchronization with the 60 hertz AC wave. There is much gain to be had by using a synchronous spark gap. I haven't built one yet. I am going to build one, and that will be something that I'll be working on here next week. When I did build the rotary spark gaps for my Tesla coil, I built them probably 6 or 7 years ago. And I built 4 of them. And while I'm building one, I figured I might as well build 4 of them because there are some people in this world who give a lot back to the community for teaching children and stuff like that. So I gave one to Jamie Oliver in Rochester, New York. I gave one to another guy on the east side of Cleveland, and I kept 2 for myself. I think that is important for us, for those of us who can build things like that as complex as a rotary spark gap, and for those who do teach, to actually donate some of our time to help others educate those less fortunate few who do not have a chance to get a better education in that arena. I'd like to thank several people for my education over the past 6 or 7 years on Tesla coils. The first one that comes to mind is Jamie Oliver. He has a website on the internet explaining how to tune a Tesla coil with an oscilloscope and a signal generator. That concept is very, very easy once you've done it. And I have to say this is not complex, but you have to apply yourself and actually do it. Once you do it 2 or 3 times, it becomes very, very easy. I have to thank Ed Wingate in Rochester, New York, for holding the Teslathons, where I met some of the most important, influential people that got me going to build this big Tesla coil. Steve Ward, I'd like to thank Steve Ward. Steve Ward has a wonderful website up, and he is I can't thank him enough. Thank you, Steve. I want to thank Jim Phillips. Jim Phillips was a guy I met probably 4 or 5 years ago via a telephone call from a guy that I knew in Cleveland. Jim now is running a school free to children. The website is tlcfund.com, and he's known as Professor Know-How. In fact, Jim will be up here next week to take a look at this. He lives in Atlanta, Georgia. He'll fly all the way up to Cleveland. He wants to take a look at this thing because he's really, really fired up about it. The Tesla coil is powered by a 14.4 kV pole transformer at 10 kVA. The ballast that is used on the 240 volt line is comprised of two Lincoln arc welders, and we're using the primary turns of the transformer to act as ballasting to limit the current to the pole transformer. I know a lot of people probably don't get what I just said, but I'll explain it to you a little bit differently. Ballast or a reactor, you can call it either one, ballast or a reactor on alternating current acts like a resistor on DC current. What it does is it limits the amount of power or the amount of current that can get to the step-up transformer. By doing that, you limit the current that the transformer is allowed to take. The transformer, if you do not have a ballast on it, will take as much power as you can feed it, and it'll actually burn itself up and catch on fire. When we use ballast and a pole transformer together as a power source, you can hook the welders either in parallel or you can hook them in series, and you can limit the current way, way down. And I mean way, way down where this Tesla coil will barely run. You can run this thing all the way down to where I have sparks that may come off of the toroid maybe this long. And then you can change the welding taps on the welder itself to actually turn up the current or turn down the current, or in parallel turn the current way down and get a tremendous amount of current through the transformer. It is very helpful. Having the welders in series or in parallel as ballast on that pole transformer, I can see why. I've read this before where some guys have actually said, I would never go back to any other way to running a Tesla coil except for using a pole transformer, because once you put ballasting with it and able to adjust that ballast, you can turn the heat way down or turn it way up, and it doesn't matter. And it is very, very easy now to run any other Tesla coil. And I'm going to show some details now. So I'm going to stop the camera and I'll show you some real close details on different aspects of this construction.